Good evening, everyone. Good evening, everyone. Welcome to the week 4 live interaction session for the course Waste to Energy Conversion. So, as usual, let's just wait for a few minutes for others to join before we begin our session for today. So, let's start our session for today. I hope I'm audible. Let me share my screen. So, good evening, everyone. Welcome to the week 4 live interaction session for the course Waste to Energy Conversion. This course is offered by Professor Prasenjit Mondal from the Department of Chemical Engineering, IIT Roorkee, under the NPTEL SWAYAM program. Myself, Pratyumnan, a teaching assistant of this course, a PhD scholar from the Department of Chemical Engineering, IIT Guwahati. So, for the last 3 weeks, we were looking at waste to energy conversion. So, as such, in this particular topic, we were discussing about the waste material, what is a waste and its classification, and the different types of waste materials. We categorized them. Then we moved on towards how to convert these waste material into energy. So we discussed a brief overview we had for all the three kinds of conversion process, which is the thermal conversion, biological conversion, and chemical conversion. So the very first type of conversion was the thermal conversion, and we dedicated almost 2 weeks in order to look at thermal conversion. And in this particular lecture also we will be continuing our discussion on the thermal conversion routes for waste material to energy. So in the previous 2 weeks we discussed on the incineration or combustion and gasification of the waste material. So today, in today's live interaction session, we will be discussing on pyrolysis process. So I hope all of you are very familiar with this table by now. So as I said even on the Friday session, that this particular table we will be using it until we finish the thermal conversion process. So, in the last two sessions, we completed our discussion on combustion and gasification. We discussed about how the value of R, which is nothing but your oxygen to the coal here, or you can also give it as a biomass, that particular ratio affects the kinds of products that gets generated out of the process. And we also discussed how varying the oxygen to the biomass feed ratio, we can alter the composition distribution. So in this line today we will be discussing about the concept of pyrolysis. So as all of us are familiar by now, pyrolysis is a process wherein the oxygen is limited in amount. So we do the process, you can say the combustion process or you can say the burning process in limited supply of oxygen, and that particular value is that the R value, or you can also say the oxygen to the biomass ratio, the feed ratio value should be less than 0.68. So, unlike in case of combustion and gasification where you predominantly get these gases like oxygen, carbon dioxide, carbon monoxide, hydrogen gases, in case of pyrolysis process, you typically get more more than only gases. So, for example, that's what is actually given here. So, oh, sorry. So, waste material. So, waste material on application of heat with the very limited supply of air, or probably you can also say in the absence of air, you tend to get three products. The first one is the gas, the second one is the bio oil, and the third one is nothing but it is the char. Char is nothing but the solid char, that the solid carbon particles that gets generated out of this pyrolysis process. So here you apply, majority of the process is typically dependent only upon the amount of heat that is supplied to the system. So what actually happens is, initially you take the material and then you increase its temperature, it undergoes first drying. So once the drying is over, the devolatilization happens. The volatile species that gets generated out of this process undergoes a secondary cracking process where these volatiles that are generated are converted to converted to gases as well as that of the bio oil. So the basic thing that we want to look here is that unlike in case of the combustion and the gasification, which is a straightforward reaction where burning the waste material along with the air and upon the application of heat, that's what I said as burning, you typically don't just get gases alone, you also get bio oil and chars. And the major reason being is that the pyrolysis process is typically, it you can you can separate them into primary phase and the secondary phase. So in the primary process, the waste material undergoes drying and then the devolatilization starts to happen. As the devolatilization process continues, volatile species are usually generated, and these volatile species, as you increase the temperature, they undergo a number of reactions which results in the formation of gas as well as that of the bio oil gets produced. So as such, when you see in the form of gas, you typically don't get CO2. So here we need to change this. You typically get carbon monoxide and hydrogen, because since the you do this process in a limited supply of oxygen, so you do not get carbon dioxide or water molecules in a majority of its proportion. So in major cases, only carbon monoxide as well as the hydrogen gases will remain. So if all of you remember carbon monoxide plus hydrogen is nothing but it is the syngas. So here also that generation will happen. However, compared to other cases like gasification and combustion, the amount of the gases that gets produced will be less. Now here we try to we need to understand that there are totally depending upon the type of heating rate. So if when I talked about the primary and the secondary process, usually this process takes place at a temperature of 400 to 500 degrees Celsius and at a very fast heating rate. So usually the amount of time that these usually the residence time for this is maintained in the order of seconds, like 1 second. So that is the residence time in which the material is actually heated. So based on this residence time, you can actually classify pyrolysis, the entire pyrolysis process, as carbonization, then you can say slow pyrolysis and fast pyrolysis, and then you have similar classification like flash pyrolysis and so on. So my question, the very first question for this session would be, what is typically the difference between pyrolysis process and carbonization process? If you see in that particular table in the course, so in pyrolysis section you typically have three different processes. First one is the carbonization, second one is slow pyrolysis, third one is fast pyrolysis. So in this particular case, if you see for carbonization, the residence time is usually very high. Whereas in case for flash pyrolysis, in case of fast pyrolysis or slow pyrolysis or pyrolysis as such, the residence time is only in the order of few seconds at max. So now, what typically what changes does this bring to the particular process? In whether does it changes the product composition or any other changes happens? And typically, to put for just if I want to put forward it straight, what is the difference between carbonization and pyrolysis? Yes, anyone? What is the difference between pyrolysis and carbonization? Are they same or are they different? So the carbonization process and the pyrolysis process typically differ in the term of the products that gets generated. So that's why if you see when I said that the residence time for the carbonization process is usually higher compared to that of the pyrolysis process, where the carbonization time is only in the order of seconds. So when you basically heat the material at a temperature of, let's say, 400 degrees Celsius at a slow heating rate, and you basically give more residence time for that particular material, the chances of the solid carbon particles that gets generated will be more compared to that of the pyrolysis process. So if you see the product composition, in case of the carbonization process, you have more solid particles uh, compared to the pyrolysis process, where you predominantly end up with liquids and gases like bio oil and gases. However, in carbonization process, the solid charge that you are going to obtain after the process will be much higher. So this is typically the difference between carbonization and pyrolysis. So typically you need to understand the difference, because once you go into the topic of waste to energy conversion, often these two terms may be alternatively used. So we need to understand that maybe both of them are actually not the same. They typically differ in the products that gets generated, the amount of residence time that each of the material undergoes the heating process in the the heating in this particular process, so on. So pyrolysis process, usually what happens is that the volatiles that gets generated breaks down, resulting in the formation of liquids and gases. When I say liquids, predominantly speaking, the bio oil. So, as such speaking, what is the difference between the bio oil that gets generated out of the pyrolysis process and that with the commercial, let's say, diesel that is available? So, there are certain disadvantages of bio oil, right, that gets generated from this biomass and feedstocks, or natural feedstocks, what we use for this pyrolysis process. What are the disadvantages of bio oil? Oh, yeah, sorry, there was some problem with the network. So the question was, what are the disadvantages associated with the biodiesel, or what are the limitations of biodiesel? Sorry, bio oil. Yes, anyone? What are the disadvantages of using bio oil? So one in this thing that I can give is bio oil has high oxygen content in them, because depending upon the type of feedstocks that they are using, so the content of so the oxygen content will be variable. So that will be present in higher proportions compared to the commercial diesel that is available. Now, how does this high oxygen content affect the properties of bio oil? I've given the main term, so now you just need to use that main term and then let me know how does that increasing oxygen content is a disadvantage for the bio oil that is generated from the pyrolysis process. So this is something we discussed prior also, right? High oxygen content means um, the HHV value, that is the high heating value, or you can also say the amount of energy that the waste material will carry, or the bio oil it will carry, will be very less. So that means for same amount of the material, so for that means for in order to basically produce a particular amount of energy, more quantity of bio oil is required. So that is, economically speaking, it is not very viable option. So that is the reason this bio oil. So these are the disadvantages of the bio oil. So now in order to make sure that this bio oil can be used as a replacement, because as you know, diesel and petrol are not renewable resources, they are non-renewable, and moreover they are actually uh, I mean, they are fossil fuels, so they are non-renewable in nature. So if you want to use bio oil as a replacement for diesel, then you need to improve upon the properties of the bio oil so that it can commercially match with the performance that the diesel usually gives to us. So in order to improve the quality of the bio oil, we basically go for different sorts of techniques. So one is the physical activation method and another one is the chemical methods. So in physical methods, you just simply do filtration for char removal, or you can also do some sort of solvent addition, or do emulsification with hydrocarbons. Whereas in case of chemical method, you actually do chemical reactions. So you basically make the bio oil to react with some alcohols, or you do more sophisticated processes such as catalytic deoxygenation. So you try to remove oxygen through catalytic process. So typically you try to do this catalytic deoxygenation either through hydrotreating method or through catalytic cracking method. So anyone, any idea on what is hydrotreating method? What is hydrotreating method, or at least the conditions? So nothing in hydrotreating method, you basically apply pressure, and you basically apply high pressure, and you pass hydrogen gas, high pressure hydrogen gas, and you carry out the reaction at 350 degrees Celsius in the presence of some sort of a catalyst such as nickel molybdenum or cobalt molybdenum based catalyst. So this is about the pyrolysis process as such. If you see, then as you as we discussed for both combustion and gasification, we also need to talk about the reactors that will be used for the pyrolysis process. So the principle of the or the type of reactors that we use for the pyrolysis process was also very common, like in case of combustion and gasification. So you have fixed bed and fluidized bed, circulating fluidized bed. Then apart from that, you basically have can anyone list me few of them? Ablative reactors. Other than that, so there is a big list. So the major principle remains as same as what we discussed for gasification, both for fixed bed and fluidized bed, and for circulating fluidized bed as well. So these both fluidized and circulating fluidized bed are usually the commercial ones, and they are easy to scale up. However, if you see in case of the other like rotating drum or probably the ablative ones, they are very laboratory um, confined, and their scaling up is still a question. So these are some of those which are basically kind of looked out as an alternative for the fluidized bed and the other commercial type of reactors that are used. But again, they have still their own limitations, and majority of them are still laboratory confined, so it will take lot of time, and lot of time has to be invested in order to basically translate the systems from the lab scale to the commercial scale. So it usually takes a very long time for translating a particular product from a lab to a commercial scale. So that gap always remains. So as far as of the pyrolysis reactor is concerned, unlike in one of the important differences, unlike in case of the combustion and gasification systems where you actually have a flow of air, here in order to basically remove that pyrolysis products as well as the gases that gets generated, you use a you use a inert gas as a system. And in order to basically avoid the use of inert gas systems, you go for the ablative reactors. But as I said, they are laboratory confined, and still their commercial viability is still a question. So this is about pyrolysis. So here we end the concept of combustion, gasification and pyrolysis. So if you have anything related to all these three processes what we have discussed so far, then please let me know, or else we can move to the next topic called densification of solids, the production of briquettes and pellets. Hello. Yes. Hello, sir. Yeah. Hello. Hmm. So you have to actually direct these questions to the NPTEL team. So if you see in that place where you actually what do you say, you might have got a payment confirmation, right? So over there you might have some email ID, so it is better if you contact them, then they will be able to guide you. I do not have much um, what do you say, idea on this. Okay. Oh, okay. So anything to discuss related to combustion, gasification and pyrolysis, all the three concepts together, any? Yes. So the main problem with all these systems is that the nature of feedstock. So even though we do some sort of a segregation of this feedstock and pre-treatment before sending them to a combustor or a gasifier or a or to a pyrolysis reactor, the problem is the nature of the feedstock do not remain uniform, and they tend to vary depending upon the batch to batch waste that gets generated. So the biomass, one of the major limitations with respect to the biomass is its uniformity in composition. You do not have a feedstock which is uniform throughout its bulk, depending upon the what do you say, in an entire bulk you can get different, not very different, but yes, there may be difference in their properties as well, and also different types of waste. Usually the biomass waste that you get, you don't really get only one type of waste, so it's actually a mixture of waste. So when you have that mixture of waste, what problem happens is that each of them will have their own properties, and coming up to a conclusion of which particular process will be suitable, or how much or what kind of quantity of gases that you can obtain through this process will not be the same. So in order to, so then the things becomes difficult, right? Since as we engineers, we should know that if you burn this much amount of heat should get generated, and these are the gases that will be produced theoretically using equations. And of course designing part is different, but at a preliminary scale we need to be able to judge on how much amount of heat will be generated and what type of gases will be produced through this process, or in what kind of distribution these gases will be generated within the systems. So however, if the feedstock is not going to be uniform, this estimation is going to be extremely very difficult, the correlation. So in order to make life easy, you need to basically go for certain processes in order to make the feedstock uniform. So the biomass feedstocks need to be uniform so that it makes our life easy, so that we can easily evaluate how much amount of energy and what type of gases and their proportion can be easily calculated. So in order to basically make sure, and it's not just about making our lives easy, but also the uniformity of the process will be increased, and you can also get the better efficiency in the process of doing this combustion gasification of pyrolysis. So in order to do this particular process, we basically go for making the feedstock uniform in nature. And how you are going to do that? We are basically going to do densification of solids, or you can say densification of the biomass waste. When I mean densification of the biomass waste, it is, I think you can actually get an idea as soon as the word densification comes. You try to increase the density of the biomass waste. So by densification, we try to make these biomass waste have more uniform properties, so that when you use them in combustion or gasification or pyrolysis, you get the efficiency of the process is improved, so that you get more amount of energy from the process, so that the energy efficiency is improved, unlike in case if when you have a non-uniform feedstock. So the major principle, or you can say densification of the solid, the concept is to increase the density of the material, to increase the fuel density, so that the fuel will basically have uniform properties and energy efficiency becomes high, or energy efficiency is improved. Or you can say, or you can also say that the energy density is increased. Now question is, if as we have all seen, if energy density increases, what will be my major advantage? Just now we discussed this concept in bio oil also. So I'm able to improve the energy density of a system. by doing some sort of a process so called as densification of the solid. Now, by improving this energy density, how it will benefit me? How does high energy density or how, yeah, that's the question. How does high energy density help the combustion or gasification or pyrolysis process as such? Or you can say, how does the increase in energy density help me as an engineer? Yes, anyone? How does increase in energy density help? We discussed this even in the bio oil that increasing that lower the energy density of the bio oil due to the excessive oxygen content basically reduces the heating value. So due to that, I need to add more amount of, or for the to produce the same amount of energy, I require more bio oil to be used up. So similarly here also, as I said that by doing densification of the solid, I am able to improve the energy density of the systems. So if I am able to improve the energy density, what it actually means is within a particular volume of the material, I can increase the amount of energy that can be generated. So that means that to produce the same amount of energy, I require much less amount of biomass waste. So that means that, let's say for example, in order to produce some megawatt some joules of energy, if you need to burn 1 kg previously, now I need to only burn around zero point 0.5, or let's say take zero point 0.2 grams. So that means that the amount of material that is required will be less. That also indirectly means that it reduces the transportation cost of the material. So the overall process not just becomes energy efficient, but it also becomes cost efficient. So in majority of the industry, these two process typically, these two things are of the prime importance to them. So they don't just want to improve the energy efficiency of a process or of their process, but they want to do that at the expense of how much, how you can do that improvement at very less cost. So it's not like trying to improve the efficiency of a process by 1%, but in order to do that, you basically exceed the amount of profit that you get by doing that improvement. So that does not make, right? That's not a viable model of business. So you need to improve the performance of a system, at the same time make sure that that particular improvement is done at a very low cost, so that the profit margin can be enhanced. So that's typically the any business idea's core is to basically improve the profit margin. So the thing why I told this here, so when you improve the energy density of the material, the amount of material required to produce the same amount of energy decreases. So which means that the amount of which means that the transportation cost and the amount of time that is required to transport the material from its source to the plant where the incinerate, where this particular pyrolysis process is done, or any kind of combustion process is done, will be reduced. So that will basically make the process economically viable. So improving energy efficiency, not just it helps in getting more amount of energy, but also it basically reduces the expenses overall. So this, so when I say densification of the solid, what I typically mean is that you take this biomass waste and then you do the densification in such a way that you actually try to get briquettes and pellets out of them. So that is the main way to do densification of the solid. So this biomass waste, they usually undergo series of process in order to form briquettes and pellets. Now, anyone who knows what are the stages of the process to form a briquette from biomass waste? Yes. How do you produce briquette from biomass? What are the four stages? It's, you can also say, four C's. It's nothing. You just take the biomass. So as in a very layman sense, if you want to see how do you produce briquette, take the biomass, compact them in such a way that they get clogged with each other or bind with each other, and basically make sure that in a particular volume more amount of the mass is accommodated. So that's how you improve density, right? So what do you mean by improving density? In a particular volume of a material, you try to increase the amount of material that that particular volume can hold, so that m increases and v remains constant, so that density overall increases. So how do you do this process of formation of briquette from biomass waste? The four steps. Yes, anyone? So it is, the first step is compaction, then the second one is compression, third one is concretion, and fourth one is concentration. So please remember this. This may be a question in your exam if any of you have registered. This may be because these questions are usually asked. As I said, the briquette production is nothing but these particles that are present in the biomass waste usually remain far away, and you try to lock these particles together. So it's just about bringing all the particles together so that you can basically improve the density of the material. So in order to do that, you sometimes, what actually happens is, so in order to do this particular process, you try to apply pressure because you need to include more amount of mass, right? And you need to actually reduce the space between two particles. So for that, one of the easiest way is to basically use pressure. So in that particular process, what sometimes happens is that sometimes in case just pressure is not usually enough, so in that case you actually go for some sort of an binders. So the major role of a binder is nothing but it is help to bind the particles, or you can say bind the biomass waste together, so that the interlocking is efficient and you can get high density. So depending upon the type of pressure that is usually applied, you can actually split the process into three different types. One is high pressure compaction, second one is intermediate pressure compaction, and third one is low pressure compaction. So depending upon the amount of pressure that gets generated, you can either form briquettes or pellets. Now anyone who knows what is the difference between a briquette and a pellet? What's the difference between briquette and a pellet? So it's typically the difference in their dimension. Briquettes are the ones which have diameter greater than 30 mm, and pellets are the one which have usually have the diameter less than 30 mm. So as I said, in case of you by depending upon the type of pressure that you use for the formation of the briquette, you can actually classify the process into three different types: high pressure, intermediate pressure, and low pressure. In both these cases of high pressure and intermediate pressure, you typically don't require the use of any kind of binders. However, in case of low pressure, you actually require binder, because the amount of pressure that you are going to put is going to be less than 5 megapascals. So that pressure is typically very less. So interlocking may or may not be efficient. So in order to make sure that if you are going to use a low pressure compaction system, to make sure that the compaction process is efficient, you basically go for using some sort of binders. That binder can typically be of two different classes. One is organic binder and another one is inorganic binders. So any examples from anyone for organic and inorganic binders? Anyone? Any examples that comes to your mind for organic or inorganic binders? Yeah, that is quite easy. Inorganic, you can say cement, and for organic, you can say starch or some sort of molasses or tar, tar particles. So these are some of the examples of organic binders. In inorganic binders, you have cement, you have clay, you have then just a second, you have you have sulfite liquors. So these are some of the examples of organic and inorganic binders. Now we need to talk about the different kind of high pressure compaction systems. So usually the main two that we are going to discuss here is, one is the piston press and another one is the screw press. So in piston press are very simple. There is a piston, you just need to keep your biomass and apply pressure using the piston. So once you apply the desired pressure, the particles get interlocked and you are basically going to end up with a briquette or pellet depending upon the type of dimensions of the die that you use. The second one is the screw press. In case of screw press, what usually happens is you have a hopper and the biomass is basically fed into the system through that hopper. Once it basically falls inside the system, you have a rotating screw. This rotating screw is the one which basically transport this biomass from one end to the other end. As it keeps going, a pressure gradient is generated, and this pressure gradient basically forces the biomass waste through the die, and depending upon the dimension of the die, you are basically going to get a briquette or a pellet out of the system. So again, each of this process tend to the process usually depends upon multiple characteristics of the biomass. So depending upon their flowability, then the particle size distribution, and then their adhesiveness, depending upon each of these process, the quality of the briquette that you obtain either to piston press or the screw press is going to actually vary. Now, so this briquettes and pellets, usually the main problem with the briquettes is they tend to generate a higher amount of carbon dioxide, and another thing is they have to be always stored under cover, and they cannot be actually what do you say, exposed to moist conditions. Any typical reasons on why this particular condition is imposed? Briquettes or pellets, they cannot be stored under moist condition. They either need to be kept under dry condition or under some sort of a cover. Why is that so? So for this we will discuss the answer. So now let me go on with this and then finish off the concept part. So once you get the briquettes, the application of the briquettes is very simple. They are basically used in some sort of a boilers or some other places where you burn the briquettes to basically release the flue gas, and then the flue gas, depending upon the temperature, outlet temperature, it may be either used to run a gas turbine and a steam turbine to generate electricity, or the after spending that flue gas, some of the flue gas may be recycled to basically be utilized for the utilized in the process itself. So this ends the discussion for the densification of the solids as well. So anything that you would like to discuss related to what we have seen so far? Anyone? If not, then we can actually move forward with the questions. Okay, if you have anything to discuss, let me know. Or otherwise, for those who are okay with the content, let's move on towards the questions. So the first question is, which of the following are used as an absorbent in PSA? How many of you know what is PSA? Pressure swing absorbent, for the removal of impurities from a gas stream. So which one of the following is used as an adsorbent? Adsorbent is a surface phenomena, absorption is a bulk phenomena, so it is adsorbent. So typically the adsorption process usually happens at the surface of the material. So which one of the following adsorbent is used in PSA for the removal of impurities? Is it silica gel, activated carbon, or activated alumina? Yes. Yes, anyone? Is it silica gel or activated carbon or activated alumina? Which of the following is used as the absorbent for PSA? Sorry, in PSA for the removal of impurities from a gas stream. It is all three. All the three of them can be used as an absorbent in PSA for the removal of a gas stream. Sorry, for the removal of impurities from a gas stream. So each of them, obviously, each of them will basically try to, what do you say, remove different kinds of impurities. Silica gel, activated carbon, and alumina will be removing different forms of impurities. For example, silica gel, it will be ethane, uh, propane, all sorts of carbon, hydrocarbons specifically speaking, and some sort of hydrocarbons, yes. Whereas in case of activated carbon, if you see, they will try to absorb methane and carbon dioxide, and in case of activated alumina, it will be just only water. So please go through the slides, these are there exactly in the slides, so please go through them. And this particular question, why it has three different answers, is because I made it in such a way to basically make sure that we get a practice on one or more than one correct options. So usually, sometimes if you've seen gate exams or any kind of exams, nowadays one or more than one correct option has become a popular choice because people often tend to make mistakes in them. So For that particular reason, I have kept all three of them as correct, and I deleted all of these options. So please look at the slides once. Now, moving on towards question 2, identify the most suitable option. Pyrolysis produces char and gas, char, gas and liquid, gas and liquid. This is a easy one. I mean, what we discussed right now. Oh. Char, gas, and liquid. Yes. So, obviously, in case of pyrolysis process, the quantity of char may be less, but char will be present along with the gas and the liquid. So, in case of char, it will be solid carbon particles. In case of gas, it will be predominantly carbon monoxide and hydrogen gas. And in case of liquid, it will be bio oil. So, I hope there is no confusion or no doubts in the first two questions. Can I proceed to the question 3, or shall I wait for some time for if anyone has any questions? Okay, so let me show you the question 3. Identify the most suitable option. Catalytic pyrolysis aims to reduce acidity, viscosity, and oxygen content, increases the heating value, produce low carbon chain compounds. Which one of the following is the most suitable option? So which one it could be? Anyone? Is it reduce acidity, viscosity and oxygen content, or is it increasing the heating value, or it is basically to produce low carbon chain compounds? Yes, anyone? Oh, Yeah. Sorry. So sorry, there was a network. This thing, I lost my network connection. So, yeah, here we were. So, question 3, identify the most suitable option. Catalytic pyrolysis aims to reduce acidity, viscosity, and oxygen content, increase the heating value, and produce low carbon chain compounds. A, okay. So that is the primary purpose of catalytic pyrolysis. So it basically tries to reduce acidity, viscosity, and oxygen content in the biomass system. So that typically helps in improving the heating value. So the since it says identify the most suitable option, it is reduce acidity, viscosity, and the oxygen content in the system. So shall we move on towards the next question? Okay. So let me put forward the next question. Which of the following statement is not true about densification? It provides simple mechanical handling and feeding. It provides uniform combustion in boiler. It reduces cost of transportation. It increases dust production. Question 4. Any answers so far or no? What will be the correct answer? I think D. Okay. Any other answers other than answer D? So option C is true about densification that we discussed. And I said, why is it so? Because energy density is increased. So uh, for a particular, so more amount of energy can be generated for a particular amount of material. So you don't need lot of quantity of material, and that typically reduces the transportation cost. So this is true about densification. Then what about the other three option? It provides uniform combustion in boiler. It is true, right? Because we said uniform properties, so the combustion as such it should be uniform. So this is also true. Now we have two options left out. It increases dust production. It provides simple mechanical handling and feeding. Among these two, which one is correct? I did say that briquette usually has one particular two disadvantages. One thing is it generates a lot of CO2 content, and it also generates a lot of smoke. Second thing is it cannot be the briquettes cannot be stored in moist conditions. So it does increase dust production. This is also true. So is the first option correct? It provides simple mechanical handling and feeding. Is not true about densification. Yes. Oh, so, okay, sorry. There are, I think, okay. This is the previous one. So, densification, yes, it does means that the handling is simple, but mechanical handling and feeding, there are also complex process, right? As I said, screw press, rotatory screw, sorry, a roller press and pellet machine. So, those may actually create difficulty. So, let's keep this question for the time being and let's discuss this, because I think it's not clear to many, right? If I'm not wrong, or do anyone have any this thing related to the answer? A option A is not true about densification. Okay, let's move on to question 5. Friability index of 0 indicates that the brittle is not is in adequate quality. Inadequate briquette quality, and both A and B, and none of this. What is friability index? Anyone? What is friability index? So usually when you deal with the properties of the briquettes as such, you have to basically be or have an understanding of three properties. First is density, second one is friability, and third one is its ability to be under moist conditions. Whether that particular briquette can survive or have that adequate quality under moist condition. So what is friability and what is friability index? So friability is nothing but it is the resistance to the mechanical shock. Friability is basically nothing but the briquette's resistance to mechanical shock during the handling of the system or during the handling of the briquette. Sometimes what happens is there may be some sort of a mechanical shock, let's say like dropping of the briquettes on the floor. So it basically determines whether that briquette have the adequate quality to resist that particular shock and remain viable and remain, what do you say, and remain useful. So that particular property is called as the friability of the briquette. Now what is friability index? Friability index is nothing but how much amount of the material or how much amount of the briquette material can be retained when they are sieved using a 20 sieve. That is what is called friability index. So friability index is the amount of material that can be retained without that can be retained in 20 sieve. So what do you mean by friability index of 0? So that means no material is going to be retained in the 20 sieve. So I said that for each briquette, a briquette as such, if you see, their diameter is going to be more than 30 millimeter. in dimension. So if no briquette is going to remain in that 20 sieve, what it typically represent, all their sizes are going to be less than 30 or you can also say that they are going to be fragmented. So all the briquettes whatever you actually densely packed, they are usually going to be in the form of fragments. So that's how they pass through the sieve. So does that mean, so since I said that all the briquettes will basically become like a fragments, or you can say the briquettes are present in the form of fragments, what does it say about the briquettes quality? Is it good or is it bad? Oh. The quality is obviously bad, right? Because none of the material is going to be retained in the seam. All are fragmented. So how? So the main purpose of formation of the briquettes itself is to basically make a compact structure in which you can improve the density of the material. But here they are all in the form of fragments. So the briquette quality is going to be inadequate. Is that fine? And how do you basically determine the friability index? You basically go for some sort of testing techniques. So one of the techniques is nothing but you put the material in a rotating drum, the briquettes in a rotating drum, or another most simple method is you take the briquette and then drop it on the floor. If it breaks, then it's of bad quality. If it sustains that mechanical shock, then it is of good quality. So this is how you determine the friability, or you can say the friability index of briquettes. Any questions? Okay, if there are no questions, then let's move on towards the next question. Identify the briquetting machine as shown in the figure given below. So this is the figure. Based on that, identify whether this briquetting machine is a screw press, piston press, rotatory press, or none of this. Identify the briquette machine shown in the figure given below. Is it a screw press, piston press, or rotary press? So this is a screw press because you have the feedstock. This is what I called it as a hopper. You have a hopper here, feedstock here. You basically drop the feedstock. It enters inside this chamber. Here you have a screw, and then upon the application of the screw, it keeps rotating, and then it goes to this other end. And here you have a heating mantle and a die. So the what do you say, the solid particles mixes properly, they melt and then they mix, and they are forced through a die. So depending upon the shape of the die, you actually get the briquettes. So this particular briquetting machine is nothing but it's a screw press. So any questions? Okay, so if no questions, then okay. So leave question 7. Try to answer question 6 and question. Oh, wait, just a second. Oh, sorry. This should be 7, this should be 8, and this should be 9. So leave question 8. Try to answer question 7 first, and then we'll go to question 9. Question 7 is very, it's a straightforward question. Based on the compaction, the type of briquetting technologies are high pressure compaction, low pressure compaction with a binder, medium pressure with a heating device, or all of this. Based on compaction, the type of briquetting techniques are. We discussed this just now. Yes, this answer is a straightforward one. Based on the compaction, the type of briquetting techniques are high pressure, low pressure, medium pressure, or all of the above. Did I receive any answers? No. It is all of the above, right? Because as I said, in case of briquetting techniques, based on the pressure, you have high pressure, low pressure, and medium pressure. So for high pressure, the pressure range will be approximately 100 megapascals. For low pressure, it would be less than 5 megapascals, and for medium pressure, it will be between 5 to 100 megapascals. So all of the above is the answer. So if check the ninth question. Meanwhile, if anyone have anything to discuss related to question 7, please put forth your question, or otherwise look for question 9. Which of the following are the organic binders used for briquetting techniques? Resins, cement, clay, sulfite liquor. Which of the following is organic binders for briquetting process? Resin, cement, clay, or sulfite liquor. We discussed about the concept of binder. Why binder? Simple. Why binder? Basically, it helps in or it aids in interlocking of the solid particles, or you can say of the particles in the biomass waste. And you have two types of binders. One is organic binders, second one is inorganic binders. So which one of the following will be an organic binder? Cement, clay, sulfite liquor, or resins? So cement, clay and sulfite liquor all are inorganic binders because their main constituent is inorganic, because they are mainly inorganic in nature. So resins is the answer. So they are the organic binders which is used for briquetting techniques. Now let's, okay, before we come here, any questions so far? And I did ask one question in between. Why should this briquettes be kept under dry conditions? Any answers for that question? So the major reason being is that the binders are usually soluble in the water. So if you provide a more moist condition, what happens is the binders may get dissolved. So in order, and the fragmentation may happen and the binder may lose the quality. So in order to prevent that from happening, the briquettes usually have, in order to prevent that from happening, the briquettes are usually stored under dry conditions. So kindly have a note, look, what do you say, keep a note of this. This is very important. Why the briquette should be stored under dry condition and not a moist condition is useful. And if you want to determine how long will this be able to survive under a particular moist condition, for that you can do immersion test. So if you have any questions to ask related to this, please let me know, or we can go to the numerical problems. So we have 20 minutes left, so I think we can do two problems. Any questions so far related to this MCQs what we have discussed? Leave question 8. Question 8 is based on the energy production. So that part I haven't covered it in this live interaction session. So along with the week 5 content, I will do it all together at once. So any questions? Or else I think we can go for the next one. Question number 10. In a MSW, that is municipal solid waste gasifier, air flow rate and feed flow rate are 10 Newton meter cube per second and 5 kg per second respectively. The MSW does not contain any sulfur, nitrogen, and chloride. The syngas contains carbon monoxide 30%, carbon dioxide 5%, hydrogen gas 35%, and methane 5%, and ethylene 3%. Calculate the rate of production of syngas in Newton meter cube per kg of MSW or municipal solid waste. So you are given the feed rate and you are given what will be there in the syngas. Now based on this you are supposed to calculate how much syngas or the rate of production of syngas. So how to go about this? So try solving it. We will discuss this question within a few minutes, but please give it a try. This is very similar to the problem that was solved in tutorial on gasification lecture. I mean, I would say it's exactly the same except for the fact that I have changed the numbers. How to solve this problem, or what formula to use to solve this problem? So anyone who knows the formula for on how to solve this question, because once you know the formula, just after that it's about substituting it there. Yes, anyone? So it is syngas production rate equal to airflow rate times 0.79, the entire expression divided by 1 minus CO plus CO2 plus H2 plus CH4 plus C2H2 divided by 100 time this entire expression times the feed rate. Is the formula fine? So now based on this formula, you are supposed to calculate the rate of production of syngas in Newton meter cube per kg. So you just need to substitute the expressions and then you'll be able to get the answer. So anyone who has the answer with them, who has already solved? Just a second, 1 minute. Okay. Anyone? So let me just start solving. If you have the answer, either you can post it in the chat box. So airflow rate is 5 kg per, oh sorry, 10 Newton meter cube per second. That I'm going to keep it as 10 times 0.79 by 1 minus CO. It's already in terms of percent. I mean you have 30%, so you need to put the same value because you have by 100. So 1 by 30 plus 35 plus 5 plus 3. This times feed rate. So feed flow rate is 5 kg per second. So 5. Now syngas production rate is nothing but 10 times 0.79 is 7.9 by uh, 1 minus 35 78 by 100 is 0.78 times 5. So syngas production rate is 0.22 times 5 is 1.1. Okay, so 7.9 divided by 1.1, how much is that? Oh, 7.18 Newton meter cube per kg. So anyone with the same answers or any different answers in case, please let me know. We have one more question to solve before we can close our session for today. So anyone, any questions? If you don't have any questions, then we can move forward, but please let me know if you have any questions. Next question is, let me just take a small question, just 1 second. Oh. Hmm. Okay, let's take question just a second. Okay, let's take question 12. So if there are no doubts, can I move to question 12? Question 11 we will take it up later. Question 12 is more important. Shall I proceed further? Anyone? Okay. So let's go to question 12. Pine needle is used to produce bio-oil in a slow pyrolysis unit. The percentage of bio-oil, biochar, biogas, biochar and gas are 30%, 40%, and 30%. Average molecular formula for biochar is given, and for bio-oil is also it is given. Composition of gas is given. They are asking calculate the percentage of carbon that has been converted to bio-oil. So you have pine needle, you are going to do pyrolysis, and out of that you are basically generating some products. That is bio oil, char and gas, and each of them are at a particular percentage as 30, 40 and 30. Now you know the average molecular formula for biochar and for bio oil. They have given the composition for gas also in terms of hydrogen, carbon dioxide, carbon monoxide and methane. Now the question is calculate the percentage of carbon that was there in the pine needle which is actually converted to bio oil. So how to solve this question? If not the entire answer, at least if you are able to get the idea on how to solve, then please let me know. That is far sufficient than the final answer. Is anyone with any thought process on how to solve? So I don't need the final answer now. I just want how do you go about solving this problem? Yes, anyone with any answers, thought, idea? So let me just give you a brief this thing idea on how to solve. So you so we know that we have to calculate the percentage of carbon in the bio oil. So to make the process easy, let's assume that let let us take a basis first. Basis that the final product that we get is for 100 grams. So once you have the basis, now it will be a little bit easy. So we know, so it's given in the question that bio oil, char and gas are in 30, 40 and 30%. So assuming we have 100 grams of product, then based on that, how much each one will be bio oil, char and gas. So bio oil will be 30 percentage of 100 is 30 grams, char is 40 and gas is 30 grams. Now you know the average molecular formula for biochar and bio oil, and you have the gas compositions. So with this you can calculate the molecular formula. How? So for molecular formula for bio oil, I'll just write for bio oil. You can do. I request everyone to do it for the other two of them by their on their own. So it is formula is CH 1.47 0.36 N is 0.005. So for if you want to calculate molecular weight for bio oil, then it will be 1 times 12, that is the carbon mass. Then for hydrogen it will be 1.47 times 1. Then for oxygen it is 0.36 times 16, plus for nitrogen it is 0.005 times 14. So if you calculate, you will be able to calculate the molecular formula for bio oil. Now from here you can calculate the number of moles of bio oil in the product stream. So that would be 30 by molecular weight of bio oil. Now once you know the number of moles of bio oil, so the C carbon that is present in the bio oil is nothing but is the number of moles, because it is 1. The amount of carbon that is present is 1 carbon. It's not like C2 or C3. So for every mole of carbon, is it fine? Or so if you see here, the thing is, whatever moles of bio oil you produce, same moles of carbon is also going to be present, because the average molecular formula is C1. So if it is going to be C2, then you need to actually multiply by 2. But since it is C1, the stoichiometric ratio between the stoichiometric ratio is 1 here. So the carbon that is present, so the number of moles of bio oil and the carbon present in the bio oil will be same. So this will be equal to number of moles of bio oil. So similarly you need to do it for char. So same process for char. When you come for gas, you need to actually, since they are also in the form of percentages, you need to convert each of them to their respective moles. And since carbon here is in 3 different products, CO2, CO and CH4 has carbon, you need to multiply that particular respective percentages to the total number of moles of gas that gets generated, and if you add all of them, you will get total number of moles. Now you know the C that is present in the bio oil, so C present in that bio oil divided by the total number of moles of carbon will give you the percentage that gets converted, the conversion percentage. So take this as a task and then try to solve. If you have any doubts, please email me, or we can discuss this in the next class as well. So any questions so far? Here you for same way as we have done for bio oil, you need to do it for char. For gas, you need to calculate these respective percentages in the form of moles. Then since this carbon dioxide, carbon and CH4 all three have carbon in them, you need to multiply the total number of moles with their respective percentages. Once you do that, you will get the C present in the carbon that is present in the gas. If you add up the carbon that is present in the bio oil, char and the gas, you will get the total amount of carbon that got generated. So then you will be able to calculate the fraction of carbon in bio oil. So any questions? Anyone? Okay. So if you have no questions, we have few more questions to solve. These we will probably take it up in the next live interaction session. So that's not a big deal. We were left out with the two questions which we were not able to solve. So that's fine. So let me just stop sharing. So if you have any questions, please let me know. The main reason we are practicing these problems is to basically make sure that the assignment is easier. So if you have any doubts over the week, then please let me know that you can email me. My email ID will be along with this presentation, and I hope all of you are able to access the live recordings as well as the presentation. I hope there is not much of a issue in that. If you have, then again please raise your concerns here. We will see to it what to do. So my email ID will be available along with the presentation, so you're welcome to email me at any time, and I'll be able to respond to that queries as soon as possible. So in case if you have no doubts, then I think I can conclude the session for today. Okay, so yeah, okay then. Thank you all for joining today's live interaction session. Our next live interaction session will be on 22nd February from 5 p.m. to 7 p.m. So I hope to meet you all there. And I also take this as an opportunity to thank Professor Prasenjit Mondal sir as well as the NPTEL team for providing me this opportunity to interact with you all on this Sunday afternoon. So till then, we will meet next week. Till then, if you have any queries, as I said, please email me. So have a great weekend ahead, and thank you so much for joining today's session. So thank you all, and have a great weekend, and bye.